What is up, YouTube? Code Different here again. This is probably going to be the final video that I make on the Lala language. For a few different reasons. One, I don't really have anything I want to add to this language. This is pretty much, after today, the extent of what I wanted to do with it. It's really just going to be a language that I just use for quick matrix operations. I used it in a class actually this past semester, which was fun. But I will not be adding anything else to it. Like today, the title of the video says I'm adding functions, and that's really the extent of what I would like to do. Instead of repeating the same thing, I could just write a function for something. I'm not going to add any control flow or any other advanced programming features. It does what I want it to do. The other reason, and these two are kind of tied together, after I started working more with the pest parser generator for PEG grammars, I realized I really enjoy Menhir from OCaml more. I don't really like PEG as much, or pest as much. Pest is fine, but I was getting some problems with left recursion and like figuring out some precedents for operators, and I decided just to not even bother anymore, because the only way to fix some of those problems were to essentially use a different version of pest. But anyway, that's like beside the point. So yeah, today we're going to be adding functions to our programming language, and basically this is what the syntax is going to look like.
What the fuck is this piece of shit?
It's a little bit of a mix between JavaScript and OCaml, where I like the whole JavaScript idea where they would have like let function equal the parameters inside of the parentheses, and I really like the arrow. I don't know, it just looks cool to me. And then everything in the actual body of the function is an expression, but the last thing is the identifier that we want to return. And you might be saying, well, what if we don't want to return something? In my opinion, for what is essentially just a very fancy calculator for matrix operations, I'm always going to be returning something, and I made this language pretty much only for myself. I'm not going to be doing operations and then just never returning something, because also this language is completely pass by value. I'm not going to be able to modify anything that I'm passing into it. And I forgot to mention the other, like the OCaml influence is the fun keyword, right? When you're declaring like closures in OCaml, you can do the fun XY thing, and also the no commas separating parameters. I like that. It makes it look a little bit less cluttered. So that's pretty much it for the syntax. We can see here I declare these. Oh, and the functions are first class variables. As you can see, I am able to return the actual function from this wrapper function. I'm able to return in the dot, which just does the inverse of the dot product. And I'll make that actually bigger for everyone. Sorry. That was fun. I like doing that. And yeah, so then I can get the function and store it in a variable. Notice here I'm not declaring it as a function with fun. I'm just saying let anon equal the result of wrapper, which is the actual function. Then I can call the function here. So let's see how this actually works. I just compiled Lala like 2 seconds ago. Lala-c examples funds, and we can see that this is the result of taking the inverse of this matrix, since the dot product of these two is just going to be x, since this is the identity matrix. So yeah, and we can also see if we just use int dot directly, it's the exact same thing. So yeah, that was fun. Now let's get into the actual code. Okay, so here we are. I'm not going to be going over the old stuff. All that is in the videos that I posted last summer at this point. the only additions are related to the functions, and I think I did make some changes to how some other stuff is parsed, but I don't remember. So we're gonna have to just hope I remember everything. So originally everything was in the program, everything was a statement or a command, but now everything is also a function declaration. It could also be a function declaration. Now, what is a fun decal? Well, we have the keyword fun, we have our token arrow, the equal sign already we had, L paren, R paren, whatever. So the fun decal starts with the keyword fun, then an identifier, which is the function name. We set it equal to the parameters. With the arrow going to an L brace, we can have any number of new lines. Then the body, which is a statement separated by one or more new lines, and then multiple iterations of these, and then an R brace. Pretty simple parsing. And then expressions, we've also added function applications. So because that's important, because assignments, which is pretty much the main expressions that are used in the language, we're always like setting a variable equal to something. Assignments, the right hand side of an assignment is an expression. This is right recursive, I believe. So here, let's say I want to say, like in funds.lala, I want to say z equals the application of anon on these two variables. So then here I can say the application is the function identifier, an L paren, and then an app param, any number of these, and then an R paren. And now what is an app param? It could be an identifier, an actual matrix, a monadic operation on anything, dyadic operation, or it could be another function application, which we would then evaluate in the interpreter. So I think what's important is we showed that the functions are first-class functions. They can be stored in variables, which means that they have to be stored in our environment. Now, this is the first real piece of code that I've added. The functions are also in our Lala type enum here, and the fun enum entry is a tuple of three things. The first thing being the function identifier, the second thing being the vector of parameters that are being added to it, and then the third thing is the vector of statements or expressions in the well, technically they're statements according to the pest file. The statements in the body of the function. And here I just made for some debugging purposes how it would be printed if I ever want to print the AST or no, when I want to print the environment, I suppose. So the parser here, we can start off with when we want to parse a function declaration. So if we go to the bottom here, we're always matching on the pairs, and if we remember from our pest file, statement doesn't get matched on because it has this underscore here. It's a silent rule. But function declaration, expression, and command, which is somewhere down here, do get matched on because none of them have the underscore in the front. They're not silent rules. So I removed the commands just to focus on this part. So when I have the function declaration rule, I basically use the same exact function for parsing the expressions. There was no reason to do anything else. I can just add a rule to this build AST from expression in the big match arm, starting pretty much right away. So here we have our function declaration. So actually what I'm going to do is take our grammar and dump it into the online pest testing area, and we can say fun x equal p1 p2. We can say let y equal p1 at p2. Let z equal the inverse of y, and then let's just return z. So as we can see here, we have some nested rules, which we could have also seen in the grammar, but this is a little bit of a nice visualization. So our function declaration is going to have an identifier, which is the function name, and the next thing in the list of parts to it is the params section, which has inner rules for each identifier. And notice if I just take them out, right, it's just empty. But here we have two things in there. And then our body has nested rules too, each of them being expressions. And we can do something like iterating over each of these and then going inside each of them to see what kind of expression it is. Here, they're all assignments up until I want to return the identifier. And the last thing is always going to be the identifier because every function ends with returning some identifier. So here we're going to say we match on our pair, which is just a rule, and we say pair.intoInner. And this is going to give us an iterator over these three outer parts, the ident, the params, and the body. So then we can just say ident is the first item in the pair, and then we initialize some params vector, and we can say our unparsed items are the next item in the pair like object, and then into inner. So what does that mean? So first we're on our identifier, and then we say pair.next, and it says okay, now we're on params, and then it says okay, go into inner, which is all of the inner things. And what that's going to do then, we can iterate over all of them, and we can call build AST from expression, and if it's an identifier, we can just push the identifier into the vector of parameters, or we can continue, which I should be throwing an error here, but like I said, I'm not really going to be adding to this anymore. And also that there is another important reason why I'm not going to be adding to this language I forgot to mention before, but I will talk about that when we actually get to the reason or the way I figured out what was wrong with this language. So then our body is the next item in the pair rule, and then we can just map build ist from expression over the body, and then collect it into an option vec, and then yeah, unwrap the big option. So that is pretty much it. I mean, the parsing stuff is pretty easy using pest. Pest is very simple, it's a nice library, but for what I want to do, I'm much more well versed in the OCaml, lexing, and parsing libraries, just from schoolwork. When we're parsing an application, let's go over here. We can say like x of a, b, right? Here, it's really just a flat list where the first thing is the identifier, and then each thing going into it is also an identifier in the same list. So we can just say the identifier is the first thing in our pair list, and then we go into the next item, and we can iterate over all of the rest of these, right? We can say pair.map. Now that we've called .next, we can do pair.map, and then recursively call build AST from expression, and then collect it into an optional vector, and then unwrap it, and then we can just store it like this. Some app, boom. Oh yeah, that I should have mentioned. Here are my AST nodes. The function is the same as the Lala type, but the application AST node has the function identifier, which is very important here. Not as important when I'm storing the function, but it could be useful, so I just left it. And the application also has the vector of parameters that I'm passing into it. So now that that's done, let's talk about the interpreter. So the first thing I'll have to add to the interpreter as I'm inspecting the AST of mine, which if we remember, if we go into our main rs file, we get the AST root from the parser, and then we pass it into our interpreter function. So as I'm going through the AST, I can definitely come across more than just these things. In fact, I can come across an AST node fundecal and an AST node app. I gotta re-say all that. If we come across an AST node function, we need to interpret this function, but this isn't like interpreting the actual application of the function, obviously. It's like we're declaring some function, which means we need the name, the parameters, and its body, and we need to store it in the environment as that Lala type that I went over before. if we come across an application of the function, we have to interpret the application, and I'm going to show these two functions right now. Interp_fun is a lot simpler than interp_app. So here interp_fun, if you remember, it takes the string, the parameters, the body, and the environment, and it's just going to store them in the environment as that Lala type that I showed before. It has the name, the parameters, and the body. And then we just finish. Like, that's it. If we need to interpret some application, then things get a little bit trickier. Now, here is where I'm going to start talking about the main problem that I had with my own way of doing things. The way I'm passing things through reference nonstop. When I started this project last summer, I thought I was being very efficient. I was under the impression, incorrectly, that references were the same as C++ references, where it doesn't like make a copy of the variable. But now I understand what references are really used for is for borrowing, and it's to basically work with the Rust ownership memory model. So this basically means A lives for at least as long as B. So what does that really mean? Here, my AST node has the lifetime A, and that's because A has to at least live as long as B. And why does that have to exist? Why does that rule exist? That's because my Lala types actually have AST nodes in them right here. You see? So if for some reason an AST node dies, there could be some kind of null pointer issue, right, that Rust tries to prevent, and this is why this exists. At least that is my knowledge on the topic when I was doing this a little over a month ago. So let's get into the actual program, and when we start getting into parts that I would change, I will mention them. So first, I get the environment, and I take the function that I'm specifying here that we want to apply, and I say, okay, if it's some kind of function, I just want the name, the alias list, and the body of the function. The alias list is the parameters that are used in the function that are like up there with the function declaration. So here in anon, I'm passing in x and y, but x and y are going to get aliased to a and b, since a and b are actually used in the function. So then I check, okay, if the params.length doesn't equal the aliases.length, then there's some kind of parameter mismatch, right? If I wanted to do partial function application, which is I don't know, could be cool. I obviously wouldn't be doing this, but I am. Now here is the first sort of issue. I clone the global environment, which is not ideal, right? If I have a lot of functions in a program, I would be cloning all of them, and a lot of like global variables, I'd be cloning all of them, and that could be bad. And the way to get around this would be to, instead of having because I clone it so that way then I could use those things in the function scope. But I should have done it like Python. Python has technically two environments. It has the global environment, which you can actually access using the globals function, and it also has the function scope. So here, let me show you. Right, here it has all of the things defined at the global scope. It has the name of our function, which is main. It has all this other stuff, whatever. But lastly, you can see it has x's too. And then if I say def fun, whatever, I can say, oh, it's not going to print. Maybe if I say, oh gosh. There, now it's going to print it. And you see how fun is also in the global scope. I should have done it like that, where my function has its own scope, just created, but I could have passed in the global environment, or I could have made the global environment hash map a global variable in the interpreter. I haven't really given that much thought about it. I'd probably just pass it into interp app as a reference, because I wouldn't really be, or I guess I could be modifying stuff, so it would have to be a reference. But yeah. Or no, it could just be me. It's okay. The main idea is I wouldn't be cloning it, but I am. And to change this, I just didn't really feel like it. So then here we're going to be mapping our provided nodes to our alias nodes. Since these are the same length, I can just zip them up, and the first element in the zipped list is going to be the parameter I'm providing, and the second one is going to be the alias. So here in our funds.lala, we're going to say, okay, we're going to have a list of two things. One is a tuple xa, and the other one is a tuple yb, right? Provided, alias. Provided, alias. So then here, let alias equal match alias node. If the alias node is not an identifier, I don't even know how it's possible, because it should only match on the identifiers as we discussed in our past grammar. That's the only way it's parsable. And then we say, okay, what is our provided node? I could have called build AST from expression, but I only wanted certain things to be able to be passed in as provided nodes. So here I'm passing in an integer. And I mean, this is all, if you want to read this, you can pause the video and read it. If I get an application of another function, I would just call interp app recursively. But yeah, that's pretty much it. I could have, I suppose, also allowed to pass in function declarations, but that looks kind of ugly. You could just define it up above, and then it would be an identifier. Now you could say like fun x, and you could pass in x, and it would just be some identifier. And I would just add into our function scope the key being the alias and the provided node being the actual value. So then here is the first issue.
And I've got to say, in all honesty, it's the biggest piece of dog shit that I have ever heard.
I had body O declared up here. Oops, up here. And that's the original body of the function we're applying. And down here I do this very annoying thing called .leak. And this was the only way I could get this to work. See, if I don't do .leak, then this for loop takes over ownership or whatever. Or no, sorry. Body is borrowed here in the for loop. And then if we scroll all the way down, our final result has this issue here. And when I first encountered this issue, I had possibly the longest day of my life fixing it, and I realized the only true way I could fix it is if I start over the entire project, or the entire interpreter at least, and parser, and stop passing stuff by reference, because the ownership rules and the borrowing was getting too intertwined, and I just wasn't actually doing things in a good Rust way because of my misunderstanding of how references worked. So the actual interpreter algorithm here is fine for evaluating functions, but the Rust side of it is not fine. And I have no idea how I would have prevented that, other than knowing how references actually work, which now I do. So yeah, I spent a long time on this, and this was actually part of a project at school, and I just didn't really care anymore. I said, okay, it's getting a leak. It doesn't matter, that fixes it. And ideally, right, this is a little bit of cope on my end, but does the memory leak really matter? Really? For me, no, right? Because the OS is going to clean up the memory that my program uses right away. It only matters if you have like a long running program, because then memory is just being allocated and allocated and allocated and leaked and not being freed. And it's like, then it matters. But this isn't, going to be running for that long, at least when I use it. Like I said, this is my little thing. And I am coping really hard, I know. But that's okay. So here I have my body, and I just leak it. Who knows? I would have had to really do things differently. And that's why I'm not adding to this program anymore as well. So then for every expression in the body except for the last one, that's why this -1 is here, I want to match on the expression. It's either an assignment or it's some function declaration that we're defining inside of the function that we're in which case we add it to the function scope, not the global scope. And same thing for assignments. We would add those to the function scope. So whatever, right, blah, blah, blah. Here, if we say, okay, last expression now is the last item in our body, that has to be some AST node, and then we want to match. Okay, if it's an identifier, we just return the value of the identifier. And then if it's anything else, we throw an error, because we're only allowed to do what do you call it? No, we are only allowed to do identifiers as our return statement. And then over here, right, saying like, okay, eval assignment, right, that's what we're going to be doing pretty much all the time when we're using functions. If we're evaluating some assignment and the right hand side is a function application, ta-da, we interp app and we say, okay, what's the result? If it's some Lala type, whatever. If we got some error, we just propagate the error all the way up back to interp. And then, if it's valid, then we just insert into the environment on our identifier that we're assigning to the result that we got over here. So yeah, pretty cool stuff. I'll show once again now that I just finished. Here is Valgrind output that I got before. We can see we do have the memory leak, unfortunately. 52,000 bytes. So 52 kilobytes. Unfortunate, but you learn the most doing things from scratch and making mistakes. Right? So let's build this. CP debug. No. Target debug Lala here. Lala -c, and that's our example from before. And yeah, that's pretty much it. Hope everybody enjoyed. I'm sorry about the lack of content, I suppose, and I'm sorry about the memory leak in my program, but it is what it is. I'm not going to redo the whole project, but yeah, that's it. Thank you all for watching. Bye-bye.